Welcome to Bite-Sized Data Science. In the previous video, we saw that the foundation of neural network was linear regression. A linear regression formula is applied to each unit in each layer, and we then apply a nonlinear function to the result. With the output of the output layer, we figured out the difference between the expected result and the calculated one, and then adjust the weights in each linear regression formula to get a step closer to our optimal model. Let's see how that works in practice. I'm using a Jupyter notebook in the IBM Watson Studio environment. Take a look at the description below the video for a URL to create a free account on that platform. The description also includes URLs for the notebook I'm using here. We start by reading the data into a pandas data frame. We see here that we have attributes that are strings and others that are numbers. Also, the churn attribute is the expected result. The next step is to extract the attribute into an X matrix and a Y vector. Before we can use the data, we have to prepare it. There are several ways to encode the character attributes. We keep it simple here and use the label encoder for categorical columns. Finally, we split the data into training and testing sets. The last step of the process is to normalize the attribute values by subtracting the means from it and dividing by the standard deviation. At this point, we are ready to build our neural network. The API we are using is called Keras. You can find more information on it at the keras.io website. We create the first layer of our model. It is done with the class dense, which simply means that all the units in the layer are connected to all the units in the next layer. If you remember from the previous video, we had an input layer, two hidden layers, and an output layer. The layer we are defining is the first hidden layer. It has an extra attribute that identifies the shape of the input layer. In this example, we see that it says that the input is a vector with 15 attributes. The first argument of the dense class is the number 8. This means that this layer will have 8 units that will each process the 15 input attributes. It also uses a nonlinear activation function called ReLU. One more thing. The dense layer has additional parameters that are not shown here. We use the default value for those. For example, there is a parameter that defines how the weights are initialized. The second hidden layer is similar to the first one with 8 units. Since it connects to the previous layer, it already knows that its input data consists of 8 values. Finally, we have the output layer that consists of only 1 unit, since we are talking about a binary choice as the final answer. It processes its 8 input attributes and generates one value that is passed through a nonlinear activation function called sigmoid. Now that we have our neural network defined, we're ready to compile it. We identify the optimizer that will be used and the loss function that calculates the error between the calculated result and the expected result. There is also a parameter that identifies the matrix used in the loss calculation. What we see here is that we have predefined choices of activation functions, loss functions, and optimizers. This means that we can try multiple functions, but more importantly, we can find out how these functions fared in different contexts by reading articles on the subject or looking at winning implementation in competitions like Kaggle. Now we are ready to train our model. We pass the training data and the training answers. We have two additional parameters, batch size and epoch. The batch size indicates that each training loop, or epoch, will use 18 values from the training data. We see that the model improves from epoch to epoch. We can now test the model with the second data set. We use the result of the confusion matrix and find the scoring accuracy achieved. We can also look at other measurements of how good the model is, such as precision and recall. Hopefully this video increased your understanding of neural networks. Keep in mind that this is a very simple example that does not take into account all the choices that must be made to get a good neural network model. Still, with this example, we now have a high-level understanding of what neural networks are. See you next time on Bite-Sized Data Science, and don't forget to subscribe.